Okay, can you all see my screen?
Yeah.
Okay. Yeah, so as I was saying, remember your state of matter? When we are talking about solid state, the particles vibrate about fixed positions, but when we are talking about liquid state, your particles instead they flow throughout the liquid. So this is what's happening in the molten state, okay? But they are supposed to be also ions. They're also ions that are flowing throughout the liquid. Okay, then after that, we have also our electrodes, which is very important in our electrolysis. These one are just the basics. So we'll move on to the difficult part soon. Okay, so electrodes, you need to know they are basically they can be inert or they can be reactive. Reactive means what? What does a reactive electrode mean?
Not inert, right?
Yeah, but what does it mean? Because inert means that basically the electrons just flow from one side to another, right? But what does it mean when it is reactive?
Like not made of unreactive metals, like uh gold and platinum.
Okay, but actually, yes, you're right. Okay, gold and platinum are those that are non-reactive. But when we're talking about reactive, for example, copper, then what's going to happen is that they are going to go through the selective discharge and they're going to be preferred over um other cations and anions to go through this selective discharge. And what's going to happen is that they are going to um they're going to form ions. Okay, so if they are non-reactive, what's going to happen is just that the electrons are just going to move from one side to another. Then nothing happens. But if they are reactive, what happens is that electrons will be given out and they are going to be dissolved into ions. So right, what you see is that the anode will slowly decompose. Okay? Not really decompose, like dissolve, sorry. They will dissolve and they'll become smaller, okay? So that's the part of the that's the part of the refining purifying of copper. Okay?
What happens if the anode is like completely like gone? Because
That's
it's
the
not inert.
that's the point. Okay, so
So
later
does
on
it
we go through we go through the um later on we'll go through this thing called electrolysis, electrolytic purification of copper, where we use copper as the anode. Okay, we use like the impure copper as an anode to get the pure copper out. So impure copper means that there's a lot of copper elements as well as other elements such as silver and platinum. Then we are trying to just derive this pure copper. So what I want is just to dissolve all the pure copper and let all the other impurities just, you know, collect at one side. Can?
Yeah, I understand.
Okay. But later I'll go through that in detail. Now it's just kind of the building up the foundation, okay? So we have our electrolytic cell. How does that look like? Our electrolytic cell looks something like that. Okay, so we first have electrolytic cell has to be made up of two parts. Okay, the first part is our electrolytes. Okay, our electrolytes allow the conductivity of electricity through these mobile ions, whereas our electrodes that form the other part of this electrolytic cell, they allow conductivity of electricity through this um through our electrodes, which is our anode and cathode. Okay? Because they contain mobile electrons. So both have different names and they both do different things. So electrical conduction is by our anode and cathode and they have mobile electrons. Okay? This allows the electrical conductivity. Then our electrolytic conduction consists of our electrolytes and they contain mobile ions. So all this movement of electricity through the mobile ions and electrons is the thing that allows this whole thing to run, the whole current to run. So if you take physics, it's like easier for you to understand. Which you both take, right? So you kind of understand how it works. Okay. Then we talk about our electro electrolysis process. Okay, this one is the important part because this is basically what the whole chapter is about. Okay, so we first have the yeah. Okay, we first have the same thing, our electrolytic cell. Okay, and for this example, we will use our molten sodium chloride. Okay, so you can see our molten sodium chloride, and you can see we are going to use carbon, which is a inert electrode. Okay, so what's going to happen is that, first of all, what's going to happen is, let's talk about step one, okay? Okay, look, you see this as a process. You don't go everywhere and make yourself confused. You see this as a process first. So what do I mean by process? We first see as the electrons flow from positive to negative terminal of battery. Okay, then the battery later we'll talk about how it works. Okay, it's actually called uh simple cell. Okay, it's made of a lot of simple cells. Okay, this is the battery. We have a positive side and a negative side. So why this side is positive is that it's going to attract electrons to it. Okay, then after that, this side is going to be negative to push electrons out of it. So you can see that it's pulling electrons out of my anode. Okay, so electrons are pumped away from anode to cathode. And what's going to happen is that now my anode, now my anode is going to be electron deficient. So it's going to attract my anions, and my anions will move to anode and give up electrons. This is when oxidation happens. And at the other side of things, we have our cations moving to our cathode to receive these extra electrons. And this is where reduction occurs, okay? Then we have the part where, so what if now the anions give up electrons? And so what if the cations take in electrons, right? So this is when we talk about how discharge happens. So for example, now our anion is chlorine, right? What happens is that chlorine, right, is going to take up chlorine from, chloride. Chloride anions is going to give up these additional electrons that they have. Okay, then what are they going to form? Okay, this is the formula. This is the ionic formula lah. Okay, but then what we want is the overall formula. So we have trouble with this, right? How do we come up with this? So all you need to know is that we cannot really leave it in this state here. Because why? Chlorine will not be like, in reality, chlorine doesn't exist like that. Chlorine exists as a gas, which is Cl2. Okay, so we need to convert Cl into Cl2. Okay, and in this case, we'll have 2Cl. Okay, so we put it in this form. So, what's here, it doesn't really matter. What's on the left side doesn't really matter. What's on the right side is what matters, because how we form our overall equation is that we are going to use we are going to find out what's our product. Okay, so our product is Cl2, for the anion side. And then for the cation side, very simple, Na plus is just going to take in electrons to give us Na. Sorry. Okay, Na can just exist in this form because it is a metal. Okay, so what I already said, right? What is on our left side does not matter. What is in our right side matters because that is our product. Okay, so when we form our overall equation, okay, so our fifth step is that our ions are going to be discharged to form atoms or molecules, okay? So how do we come up with our overall equation? All you want to do is you want to take the reactants first and then also write down the products, okay? So I already know what are my products, right? My products is Na in the solid state as well as Cl in the gaseous state. Okay, so can someone tell me what was the initial reactants?
NaCl aqueous.
Correct. Okay, Jeron, understand this part?
Yeah.
Okay. Then next part, we talk about electrolysis of molten ionic compound, which is the same thing we just did. So I'll just put this down here. This is the same thing we just did, but what about our electrolysis of aqueous ionic compound? That is the one that we need to take more note of. Why? Because we have now two different types of electrolytes, which is our water and also our sodium chloride. Okay, so I think most of you already know. I think both of you already know that what happens is that OH minus will be discharged in preference to Cl minus. H plus will be discharged in preference to Na plus because of the ease of discharge, right? Okay, so once again, OH minus is going to form. Okay, for OH minus, right? The form that is going to take in the reality is H2O and OH. And sorry, H2O and O2. So these are the two products that we care about. Okay, then H plus is going to take the form of H2. So these two products we write down. Okay, we're going to write down all these products and then our reactant is actually H2O. Okay, so we will have a lot of H2O lah, so we will cancel out. That's why at this part here, there's no H2O anymore. Okay, then selective discharge. I think I discussed this before. Okay, selective discharge is when we are talking about what's going to be discharged in preference to the other ion. Okay, so we have these three factors of consideration. Okay, so position of metal in a reactivity series is this side of the cations here. So which cation will be discharged in preference to another. Then we also have relative ease of discharge of anions, okay, which is this side here that we are talking about. Okay, but for your second point, right, if there is more concentration, okay, that is going to take priority. So this third point takes priority over the second point. Okay, now is the confusing part, right? The industrial application of electrolysis. Okay, this one just take note and write down notes if you all need to. Okay, electrolytic purification of copper using aqueous copper sulfate. So I think the question is that why do you need to use copper sulfate, right? Why do you, like, if you're just trying to get copper from your electrode, then why do you still need to use copper to sulfate? And why do you need to use copper electrodes? Okay, so let me just explain this in detail. Okay, so what we're trying to do here, right, is that we're trying to derive impure copper. Sorry, we're trying to derive pure copper from impure copper. So it's going to look something like that. Okay, we got your impure copper. Okay, so this is an alloy, right? Where we have your copper metal mixed with a lot of impurities such as silver as well as platinum. This is impure. So through electrolysis, we want to derive your pure copper. Okay, so what we're going to do, right, is that this is going to form your anion, your anode. This is going to form your anode, and this is going to be like your cathode, what is going to be deposited on your cathode. Okay, so how does that work? Okay, so we can first look at it this way, okay? Definitely, since we want to obtain pure copper, right, what we have to do is first we use an impure copper as the anode. And then our cathode, we're going to put pure copper, okay? So first of all, what's going to happen is that since electrons move out from the impure copper to the pure copper, um, we have this whole system going on, which is the same thing as what we have been seeing. Okay, but the difference is that copper is a reactive electrode. So it's going to give out electrons and at the same time dissolve. Because your other electrodes, right, what's going to happen is that they just give out electrons, but they do not, sorry, your other anode, they give out electrons, but they do not dissolve. But because copper is reactive, it's going to give out electrons and at the same time dissolve to form an anion. Okay, so from a copper, form anion. Sorry, cation, form cation since they give out electrons. They're going to form cation. So this cation, right, what's going to happen is this cation is going to move over to this side of the, this side, which is the cathode, since it is positive, right? And your solution already has Cu2 plus. But the one that is going to be discharged is not the Cu2 plus from the aqueous solution, but rather the Cu2 plus from the anode. Okay? So it's going to take up your electrons from this side and form copper, pure copper. So you can see that this side is going to build up. It's going to build up pure copper, whereas this side is going to dissolve. Okay, so can I ask, why do we still need to use copper 2 sulfate? Why do we need to use copper 2 sulfate as the electrolyte? Jeron,
I also don't know.
do you think it's weird that they need to use copper 2 sulfate even though there is, like, even though we already have the copper cation from the anode?
Is it because the copper like in the which is molten, right? We know this is aqueous. In the aqueous thing,
Aqueous.
right?
Yeah.
The copper inside that is the one that goes towards the it goes towards the anode, doesn't it? Oh no, the cathode, right? It goes to the cathode and then it erects, it does that thing, right? Then the impure copper, the copper from the impure copper replaces that copper that reacted already. So the liquid stays the same. Is that why?
No, actually it's a different thing. Instead, right, the copper from the impure copper is going to discharge at the cathode. Because what we want to do is that we want to derive pure copper from impure copper,
Yeah.
right?
Uh,
Okay, but the reason why we use the electrolytes as copper 2 sulfate is because if we use, let's say, if we use sodium sulfate, okay, if we use sodium sulfate, what if sodium, right, since it is a cation discharge, it's going to form sodium and then it's going to make it impure again. This side is going to be impure again.
then why even copper sulfate? Why not just put what like water?
Why you just put water? Because then because water is like is a weak like it's a weak conductivity of electricity.
Oh,
Okay, we talked about this
okay.
before. It's very weak. It cannot really conduct electricity. But when you put in ionic compounds, when you put in a salt, that's when it makes everything, the conductivity of electricity strong because of the mobile ions. Okay, but we can only use copper sulfate because we do not want to contaminate the pure copper that we are going to form here. So in any case that the copper from here does not get discharged, right? At least copper is going to be discharged by the aqueous solution.
But then why sulfate? Does S
Or
only
sulfate
for
doesn't really matter. In this case,
well,
sulfate doesn't get discharged at all anyways.
so it's kind of useless in a way.
Yeah, we are just trying to put in a salt.
Oh, so
Okay?
for that it could be anything but the metal has to be copper.
Yes, correct. Yes, the
Okay,
metal has to
okay,
be copper. Okay?
okay.
Zoe can understand?
Why does the sulfate not matter?
Because sulfate in this case doesn't even get discharged. The only thing that gets discharged is your copper anion. So your copper anode. Your copper anode is going to discharge and give up electrons and dissolve to form copper 2 plus.
Oh, okay.
Yeah, so you can see that usually at this site here, right, your anion is going to be the one that's being discharged. But in this case, nothing gets discharged except for the copper anode.
Oh, okay.
Yeah, your sulfur is not giving out any electrons in this case. Neither is your OH minus. We are just putting it as an electrolyte so that it's able to conduct electricity. Okay?
Okay.
Yeah, and your copper, we don't want to use any other metal cation because it might discharge and then contaminate your pure copper. Okay? So this is also used in other processes. For example, electroplating is kind of the same thing. Okay? Under industrial usage, right, we also have something called electroplating where we do the same thing, but we use so electroplating is like, let's say we want to kind of cover an object with metal. Okay? To like reduce maybe we want to prevent rusting. So we use copper because copper cannot really rust, right? It can't really react with oxygen and water to rust. So in this case, maybe we want to plate this mug here with copper. So what we do is that we are going to use copper, here a plating metal, which is maybe copper. Then same thing, this thing is going to dissolve, okay, and then it's going to dissolve and give out your um electrons so that it goes over to this side. Then now this side here, this mug here have like more than enough electrons. Is going to discharge the copper 2 that flows to this side. Okay, then copper 2 that gets discharged is going to plate this object here. Okay, then once again, your aqueous solution, right, you cannot use any other metal cations other than copper because it might get discharged and then it's going to be impure again. So in this case, we want to make sure that the aqueous solution here uses copper cation as well. Okay,
Wait, isn't this just the same thing as electroplating? Isn't it the same thing as the one you said just now? It's just that the cathode
it
is
is the
instead an
same.
object.
Yes, it's the same thing, okay? But they might phrase it. So the thing is that, yeah, this thing is exactly the same as this. But in this case, electroplating can use a different kind of metal, plating metal. So it doesn't have to be copper. But this one here that I'm talking about, right, this is mainly purification of copper. That's why we need to use an impure copper as a anode and pure copper as the cathode. Okay, but electroplating can use any metal you want. Any metal that that's reactive lah. Okay, then now we talk about simple cells. So simple cells is the thing that is in your batteries. Okay, so it's in these batteries here. So they are the thing that allow your whole conductivity of electrolysis to happen. So simple cells basically is just another electrolysis system that's going on. But in this case, they are going to use two different metals, okay, of different reactivity. Why do we use two different metals of different reactivity? Anyone can answer? Zoe?
I have no idea.
Okay, so they use different metals of different reactivity, right? For example, zinc and copper. Zinc is the more reactive one. So in this case, zinc is going to go through oxidation. Okay? And zinc is going to go through oxidation to give out the electrons. Okay? In preference to copper. Copper in this case will not give out electrons. Since zinc is more reactive, what's going to happen is that it's going to give out its electrons, and these electrons are going to flow to copper. So copper don't give out. It takes in your electrons. Okay? And since now it has more electrons than sufficient, it's going to give out these electrons to the electrolyte in this case, which is dilute sulfuric acid. Okay? To your cations, and that dilute sulfuric acid will have H plus cations. And H plus cations will be reduced by taking in the electrons to form H2. Okay, so you can see that the two products here is your H2. It's actually just H2 lah. Okay, and this is like kind of your overall equation. Because we have zinc, which is one product, and the other product is your dilute sulfuric acid. And then after that we also have zinc and sulfuric acid left, because there will be, when your zinc dissolves, it's going to form Zn2 plus, and when your H plus gets discharged, it's going to be left with SO42 minus. So zinc and SO42 minus will kind of react to form zinc sulfate as a product. And we also have your other product, which is H2 plus. Sorry, H2 gas. Okay? So this is your zinc copper cell and that reaction. Then if sometimes they'll ask you for the ionic equation. So this is a chemical reaction. But if you want the ionic reaction, we need to separate all your aqueous solutions. So your H plus, which is AQ, as well as your SO42 minus, the AQ in this case also. Okay. Your zinc 2 plus, AQ, and your SO42 minus. And your H2 is just gas, so we do not separate it. Okay, then cancel out all the spectating ions, which is SO42 minus, SO42 minus. We just get that zinc plus 2H plus and zinc 2 plus. So it will give you zinc 2 plus AQ and H2 plus gas. Okay, this is our ionic equation. Okay, any question? You know, we'll move on to doing some electrolysis questions. Any questions, Zoe or Jerome? Is it clearer now for you? Zoe, is it clearer, like the explanations?
Yeah.
Okay, what was the question in your prelim that you had trouble with, the electrolysis one?
Basically, they combine both electroplating and simple cell. So it got like really confusing.
Simple cell is just part of the battery part, right? So it's not really in the electrolysis.
No, like they connect the simple cell to electroplating. Yeah, you know, like electroplating, you need like power source. So that power source was the simple cell.
Yeah, correct.
Yeah,
That's what it means. Yeah.
It got confusing.
Okay, we'll try a few questions. Actually, when you get back your paper, then you just show me, then after you can go